Okay, in the tradition of recursive logic and the type of logic that was pioneered by Kurt Gödel, I want to try a little experiment here, so bear with me. Hopefully this will work out. We're going to take a statement G, and the G statement refers to itself, and the G statement is this statement is a new statement with respect to the system. Meaning this statement that I just made, obviously, in other words, quote, this statement is a new statement with respect to the system. Okay, well, if that statement is true, then it's a new statement with respect to the system. If the statement is false, then either it is, the statement's never been in the system before, and, it's the very first time that statement's been, the statement is not in the system. In other words, it's false, therefore it's not in the system, in which case, yeah, it's a new statement with respect to the system. It's contradictory if you say that it's false in that way. Now, if you say that it's, in other words, let me put it this way, there's system U that has a certain set number of statements, and I'm now introducing G as a statement that is new with respect to system U. If I say that it's false, either it's not in system U at all, in which case, by introducing it, it is in fact a new statement with respect to the system, or it's an old statement with respect to the system. But then if it's an old statement with respect to the system, it's true. But then it's true that it's a new statement with respect to the system. Okay, so self-evidently, using very strict binary logic, leaving aside multivariate logic or anything of that nature, I have, basically, it's not that I'm so brilliant or anything, I basically restated Kurt Gödel's incompleteness thesis. Rephrasing, instead of saying that the system's incomplete, I'm saying that you have a new system with a new statement with respect to the system. That's basically a way of stating that I have axioms that are unproven with respect to the system potentially existing. Okay, now I want to take a different spin on this, and obviously you could go through the whole deal with Gödel numbering system, and actually I'm going to do that in a minute and come up with an interesting result. Let's say that I introduce okay, I have my statement G. This is a new statement with respect to the system. Now I'm going to introduce a new statement with respect to the system. I'm going to say this is a new statement with respect to the system. Okay, in other words, I'm doing it twice now. Well, here's a problem. Unlike the incompleteness theorem, this seems to break down because I just introduced this is a new statement with respect to the system twice. Now, with the Gödel numbering system, I do not have a new statement with respect to the system. Mathematically, what I've just done is meaningless because it's an old statement with respect to the system. It's, if you look at it in the way of Gödel numbering. And yet, philosophically, it is a meaningful statement. Mathematically, no, it isn't, but philosophically, yes, it is, because you can make each of these, this is a new statement with respect to the system statements. You can have a one-to-one correspondence with an actual system of philosophical thought, and then have make the first one correspond to a new statement, and then the second one correspond to a new statement again. Or even in our daily lives, we may eat an apple, but each time we eat an apple, it's a new apple. I mean, let's say I ate an apple today, and that's a new thing. Well, tomorrow you eat an apple again. So actually, pragmatically, yes, you can have newness with the same exact statement. And in our practical lives, we would have that. Now, how would we handle that in the way of Gödel's system? Well, we would have to essentially redefine the rules of Gödel numbering each time we would do it. The first statement, we would have one set of mathematical ways we would convert our letters into numbers, and then have some kind of mathematical system. And then the second time we would have to have a different way of converting our symbols into numbers, or we're in big trouble. It's not like incompleteness where, yeah, sure, I mean, it's when we start talking about newness, well, even with incompleteness, you do have to redefine the rules, but incomplete doesn't become contradictory necessarily when you repeat the statement twice, but new would. Now, what would be a way to do that? Well, you could have a mathematical system based on the sieve of Eratosthenes, where your first statement in the system, you would have corresponding to the number 2. And then you would have, if those of you who don't know about the sieve of Eratosthenes, it's a system of deriving prime numbers where you can literally derive any kind of prime number in existence starting with the number 2. Multiples of 2, okay, 2, 4, 6, 8 are excluded from the system. But then you have 2 is included as a prime. Then the next number up from 2, you have 3. And that's counted as a prime because was unknown with respect to 2, so to speak. It's not a multiple of 2. And now it's included in the system. Then you have your multiples of 3. Well, now you have 5 as your next unknown with respect to the system, but then that's included in the system. That is new to the system. 7 will be new to the system. And you can actually calculate what's going to be new to the system based on a certain set number of primes. If I have 2, 3, 5, 7, then I know what all my primes are going to be up to and including 7 squared. And then I've got to go to 50, 51, which is a multiple. 50 is a multiple of 2, 5. 51 would be 3. You don't know 17 yet, but you do know 3. Okay, then 52, well, you don't know 13, but you know 2 and 2. Then at 53, you have a genuine unknown with respect to the system, where you could actually figure out all of your primes up to 53, but not 53. That's your unknown. Well, the Greeks proved that there are infinitely many primes. And so we now have infinitely many potential unknowns in the system that will yet be included in the system, and then redefining what is known in the system as you include them. So you now have to preserve newness, you have to redefine your mathematics each time. Okay, no, that's easy enough, but here's the catch, and that is you have an algorithmic way of doing it, but not when you jump steps. In other words, we don't know if I choose the number 5,500,000,000 and yada, 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 something like that. I can know if it's a composite number, if the number's even, or if, let's say, the digits add up to some multiple of 3. And there may be little theorems in number theory that could help me figure out if it's prime or not. But there is no surefire guaranteed way of just picking any number way up there and knowing if it's a prime or not without some kind of algorithm or some kind of rubric for doing that. Primes aren't like even numbers, or they're not like square numbers where you have an easy way of figuring out what they're going to be. There's a certain randomness in terms of what number is going to be determined to be a prime. Now, this is 2010. When this video is seen, there might be some proof of maybe something. If the Riemann hypothesis is proven by the time you see this, maybe that will change. I don't know. But as of now, what number is a prime is random unless you apply the algorithm. So in a sense, what a new statement would be, according to this system, is there's a certain degree of randomness and unknowableness to that makes knowing if you're now what this is true mathematically. What philosophical implications would this have? Would it mean that that it is impossible to really prove through an algorithm what the next development of human thought is going to be? Or let's put it this way: we wouldn't know that, but is it possible? Is it knowable whether human thought is knowable? Is the question that I'm really asking. Can we take this new take, or maybe it's not such a new take, on Gödel's incompleteness and apply it to what is ultimately knowable about what is going to be knowable? And I would answer that the knowable in 100 years in the future is not knowable now. In 1900, we thought physics was knowable, and sure enough, Einstein came along and the quantum physicists came along, and no, it isn't. So what I'm going to argue based on this is not just that there's incompleteness, but even the concept of newness has a certain degree of non-algorithmic quality to it when you get up to a certain point. And I think it would sort of, in a way, go along with what Penrose is saying about the human brain maybe being able to take intuitive leaps that bypass algorithms, because the human brain maybe can figure out what the next step's going to be. And that makes, unlike a strict algorithm, which can only go step by step in a lot of cases. So maybe you can punch a hole in this one. I'd be curious to see what the comments are. Thank you.